So this is as far as the broad way that we do, but there are some additional, we want to make the system very, very good, right? When I say something, I want it to be recognized very well, right? So today we have the Alexa, the Google Voice Assistants, and so many things, right? So we want also similar things for Indian languages and so on, right? So we want to build extremely good systems that are robust, that work well almost all the time, and therefore we have a little, this is the big picture, but we of course make it very, very complex, where we have to get best performance out of these systems. So broadly, these are few things that happen, and you should understand why that is so. So remember, phonemes are the hidden states, correct? So we model phonemes in terms of the states, right? And what happens is, when I say a phoneme, I don't usually say it in isolation. I don't say ah, e, oo. I don't say like that. I'm speaking naturally, that there's a flow in the sounds. Just like, I don't write it with isolation, right? When I write it very fluently, right? So there is, a cat is written like this normally in handwriting, rather than this distinct there is a distinct space that tells me the characters are separated. That happens in printed, but not when we handwrite, when you do handwriting, right? So phonemes also have this idea. Okay, so one of the first things is they are influenced by the context in which they occur. Okay, so therefore, instead of so what do I mean by that, right? So if you look at this cat versus pat versus rat, right? So if you look at it, this is in handwriting. Okay, if you look at it in handwriting, even though this middle guy is always a, it looks different, right? And that is because the letter A is influenced by the left and right context, right? So depending on, so nature makes it very fluent, right? So I don't take out my pen, right? I write it fluently, right? So that influences the way the A manifests itself. So there are two ideas that I'll talk about. One is, the first is a three-state model, okay? Three-state model for each phoneme. Okay, what it means is, I don't have one state for year, I'll have three states for year. That is, each state is modeled with three states for each phoneme. And what do they capture? The transition from the previous sound then the steady state part of the sound, and third is a transition to the next sound. See, there should be two sound. Okay, so this is sort of from the previous sound this is a steady state transiting to next sound. Okay, so this is essentially why we find that this modeling works better, and so this is something that we routinely do in all of our speech processing. So we model each of the sounds with 3 states. So this is one idea. This is a 3-state model. Okay, so every phoneme is modeled by 3 states. Then we have the idea of context dependency, or also sometimes known as triphone model. Um, there are pentaphone models, but quinphone it's called, quinphone. Okay, I'll not, or sometimes context dependent phones. What this means, okay, by the way, before I forget, each one of this will be modeled, each state, each of these 3 states will be again modeled by a mixture of Gaussians. Okay, so GMM for Y1, GMM for, or GMM for or something else if you want, if you're confused. If I'm talking about the O sound, GMM for OW1, the first state, GMM for the O, right? No, right? O for the second state, and GMM O for the third state. So you will have 3 states for the sound O itself. Okay, so this is one part that you have to. This is one way we make the model a little more complicated, and that helps improve the performance of speech recognition systems. The other is what's called the triphone model or context dependent models. Triphone because we will see that we are using the left and the right context, and this is inspired, like I said, from this idea that if I am talking about cat, right, rat, right, versus something like completely different. Let me put map. Okay. Sorry. Okay. What in handwriting you will observe, we have talked about this, recall. So, if you look at this, right, this looks probably, this A looks different than probably this A, right, compared looks different from this A, right, and that is because the left and the right are different. Okay, so what we are saying is whenever you have the left and the right different, it's better to have a separate model for the word, for the letter A. So in handwriting we use a separate model for A depending on left and right context. Okay, so we use a separate model for A depending on left and right context. Okay, similarly, influenced by this, similarly in spoken models or spoken language, for every phoneme, okay, depending on left we have a separate model. Okay. So, just to summarize what I said, okay, each phoneme we have 3 states. Now, there are, let us say, 44 sounds, okay, 44 sounds or phonemes. Okay. So, this is a model, right, a 3-state model, right. Now, for each 44 sounds, so let us take the sound A, right. This itself will have R1, R2 and R3, because we always say 3-state, transiting, steady and transiting to the next. Okay. Now, this itself will be influenced by what was the previous sound. So, let us say previous sound was p and next sound is pan or something, n. Okay. Next sound is n. Okay. Now, this will have one model. Similarly, if r and then transiting here, again green, so there is no confusion. I will maintain the same thing, right. So, I need green. Again, I will have AH1, AH2, AH3, and then it is going to, what did I say next? I forgot what I said. Ran, right. So, I will have na, right. So, this is now I will have separate 3-state model for R with left p and right n. So, now I will be putting here minus p plus n, p minus plus n, p minus plus n. Here I will putting r minus plus n, r. So, the left is r. So, this is a shorthand notation that is historically used. So, there are 2 separate models I have built for the sound a with the left context. One of them will have left context p, another will have right context n. One of them will have left context r, another will have right context n. Similarly, I can go through all the phonemes. So, can or something. So, I will have sir, or I can even put per that side, right, cap, right. So, then again I have this guy, right, and again I have AH1, AH2, AH3, and then let us say cap, right side comes per or something, right. So, now again it will be sir plus p, sir plus p, sir minus plus p. So, this is another model. So, the sound for phoneme left, if there are 44 phonemes, right, left any 43 can come, right any 43 can come. So, there are 43 into 43 models for separate models, each being 3-state. Okay. So, 3-state comes from this, and the left and the right context we say the way the sound manifests itself. When I say pan versus cap. These two we think are going to, the is going to look very different. So, we will have a separate model. The acoustics are different. So, we build a separate. When we say separate model, what? We are having a separate Gaussian mixture. So, I have to compute the means, the variances, covariances. So many parameters, right? So, what is making a model more complex? More and more parameters to model the variations, right? And so, this is for only one sound. So, similarly, I have to do it for all the 44 sounds. So, you will get each time 43 into the 44 different sounds into 43. So, approximately 44 cubed, right? And those are the kind of different models we produce, but because of data insufficiency, we don't usually have enough data. Nowadays, of course, we are talking about 200,000 hours. Google is talking about such a huge amount. By the way, we don't have that many hours in Indian language. For example, our lab is generating about 500 or 1,000 hours. We are slowly trying to get to more than that for Indian languages, which is public. See, we are academics, so we want people to work on it. We want to give the data freely. So, the data that we have, anybody can use, right? Unlike the big companies, because that becomes proprietary and it's probably the client data, and therefore they cannot put it in the public domain. But whatever the academics generate, these are supervised data. So, there's a lot of effort going on from various labs to make available data, right, which is nowadays they say data is the new oil, right. So, for people to work on and improve systems. So, we are struggling with 500,000 hours of transcribed data, obviously, because this is something that we have to put in the public domain, and so then it's very difficult to collect such kind of data and annotate and so on, right. So, because of data insufficiency, so we reduce the number of models by using an idea called state tying. I will not go into this details, right, which is basically some way of tying the models. That is, physically there are, or in terms of unique parameters, there are only few models, but 2 or 3 models share them, right. So, they are tied, right, share the same model. So, 2 or 3 different models share the same set of parameters kind of thing, okay. So, this is the basic idea of a GMM HMM. So, I will try to sort of show you at a very high level what is happening, okay. I will leave a lot of this is just, so this is basically the case where we are talking about for the word cat, right. So, these are the transition probabilities, right. So, where k is a phoneme, k, e, t, and each one has been represented by one state, right. So, the same thing, and so this is how we were talking about this alignment and so on. So, remember when I said the word yes, so the this is the waveform. So, if you can see, this is the waveform, and this is called the spectrogram. If you recall, first few lectures we do the short time windowing and take the Fourier transform, the magnitude, from which we extract the log Mel filter bank features. These are O1, O2, O3, O4. These are the feature vectors, and we know that these are the sounds that are there in yes, but we don't know which sound or which vector, feature vector belongs to which sound. So, that is something that you have to figure out, right. And that is the observation probability part, and that is captured here. B silence, what is the probability of silence generating the observation O2, that is given by the observation, and these are the transition probabilities, and this is called a left to right model because I usually when I am speaking, there is a sequence that goes in only the forward direction. You are evolving in time, right. So, the time is progressing, right. So, therefore, I go from when I am saying yes, there is, when I come to the sound for the word S, I never go back to yeah again, right, never, right, because I am saying yeah, s, right. So, after I reach next sound can be continue to be in which is this self loop, or I go to the next sound s, right. So, this is what I have been talking about in the previous few classes, and this is for the no, right. Then we talked about this idea of monophone versus triphone, right. So, if you look at this is called a triphone or the context dependent phone because it is dependent on the left sound and the right sound. So, this is a context dependent HMM or a state for the sound k, This is for the sound k, that's why it's in bold. This is for the sound a, and this is for the sound te. Okay, the k has a different state because the left is silence and the right is a. If the left was silence and the right was is k followed by e, keep, right, instead of cat or something, right. So then this model will be different. That's what you're saying. Depending on the left and the right context, we can have so many different models, right, and that is basically how we are going to model. So if I say like the American way, instead of you're saying yes, or colloquially, yeah, 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 right. So y, yeah, and a, right. So now you will see that yeah itself has a 3 states, because we are saying that there is a transition from the previous sound, steady state, and going to next sound. That's the 3 states. But like that, this is specifically for the left context being silence and the right context being a, right. There could be another case of yes. Instead of yes, I could be saying yippee, ye, right. So then the right context will become IH, so that will be a different model. So we are making more and more complex model, which means more and more parameters, more and more GMMs, and therefore if you have enough data, we do better and better job, right. And so this is the basic summary of what happens is a single phoneme, one model for the phoneme, one GMM, which is a single state, or I can have 3 states, 3 different GMMs for the same sound, one phoneme. So there will be the transition from the previous state, steady state, and final state. So if you look at this, there are 44 phonemes. Each of the phonemes will have 3 states. So 44 into 3, which is 132 different states. Each state is going to be modeled by a GMM, a Gaussian mixture model. Or I can go finally that I'll have 44 into 43, 43 into 44 into 43, so many context dependent phone models. Each phoneme with the left and the right being different, I'll have a different model, and each of them will be modeled by 3 states. So here it is only 120, 132, here it will be 44, 43 into 44 into the right 43 into 3 states. Okay, so that's a huge number of parameters, and that's why we do something called state time. Okay, so I will stop here. Okay, and we will now talk about next class an important topic which we call as language modeling. Okay, and what is the purpose of language modeling and so on, I'll discuss, and then we'll just wind up this GMM HMM and move to deep neural networks. Okay, so thank you.